Okay, today we are going to be solving problems as far as complex numbers is concerned, and today we are going to be facing the Cameroon GCE 2024. That's June 2024. The Cameroon GCE. It came twice in that year. It came, that's of course paper 2, question 7 Roman 1, and it also came in question 10, Roman 2. Well, so we are going to, of course, start with the previous one, or the earliest first. So June 2024, question 7 Roman 1, we are going to be solving. So we have been given a statement that says a complex number z satisfies the equation z on z plus 2 equals 2 minus I. So we've been given a statement. Our statement is z on z plus 2 equals 2 minus I. Now we have to look for the value of z in the form a plus b I, where a and b are real numbers. Now, for the sake of understanding these notes, we are going to keep our solution per se in red ink, and the explanations I'm going to use blue ink for understanding purposes. Now, given this statement, we are going to start by multiplying both sides by z plus 2, which means we'll end up with z equals 2 minus I into z plus 2. We open the brackets here. We'll end up with 2 times z, so we of course get 2z. 2 times 2, that's 2 times 2, we get plus 4 I times z. We have negative iz. I times 2, we get, will be minus 2i. So I'm going to carry everything that has z to the other side, to the left hand side, so that we will end up with something like z minus 2z minus plus iz to be equal to, here we are left with 4 minus 2i. Now from here, z minus 2z will end up with negative z plus iz to be equal to 4 minus 2i. Here we can factor out z. So if we factor out z, we'll be left with negative 1 plus I equals 4 minus 2i. Now, I don't like having negatives in first place, like you see in this negative 1. So I'm going to rearrange it into 1, or rather, I minus 1 to be equal to 4 minus 2i. From here, we are going to divide both sides by I minus 1. If we do this, I minus 1 cancels I minus 1 on the left hand side, and our solution continues as z will be equal to 4 minus 2i on I minus 1. Now, this statement, of course, if you've been solving complexes with me, by now you've discovered that it almost always ends like this. So realizing the denominator of a complex really should not be a problem at this point in time for advanced level students. So we're just going to have to multiply the numerator and denominator by the conjugate of the complex. That's the complex conjugate of the denominator, which of course in this case is I minus 1. We just change the sign, separating the two segments, that's the imaginary section and the real section. This will give us 4 times I, so we get 4i. 4 times 1, we get plus 4. Negative 2 times I, you are going to end up with a negative 2. I times I is I squared. I squared is negative 1. That is actually the fundamental concept of complexes. Square root of negative 1 equals I, which implies that's if and only if I squared is equal to negative 1. This statement, you cannot forget it. That's why in my notes, if you look at the top here, I have it on every page of my complex. It is the fundamental idea as far as complexes is concerned, or complexes are concerned. Now, continue with our solution. We were at the point of negative 2 times I, where we got that negative 2i times I, so we got negative 2, the I multiplied with the I to give us I squared, which is negative 1. Then negative 2i times 1, of course, you're going to end up with minus 2i. We have all of this divided by, now here we are going to get difference of 2 squares. That's the whole idea. That's the whole idea of multiplying numerator and denominator by the conjugate of the denominator here. So if we are getting difference of two squares, it means it's going to be I squared, and I squared is of course -1. Then we have minus difference of two squares, of course, 1 times 1, end up with 1 squared. This gives us, so we have 4i minus 2i, we end up with 2i certainly. And now we get 4, -2 times -1 is 2, so we get 4 plus 2, that gives us 6. So we have 6 divided by -1 minus 1, of course, -2. We can factor out 2 here, so we are left with I plus 3 divided by -2, where the 2's can cancel. You are left with -I minus 3. If I write that more decently, we'll get -I minus 3. So technically Z is equal to -3 minus I. This is actually in the form expected of us, A plus BI, where we can say A is going to be -3 and B will be -1, but stating it is not necessary. This is what they expected as a solution to this question per se. Now we move on to the next one. Moving on to the next problem that we are supposed to solve. That's June 2024, still question 10 Roman 3. It says using the Moivre's theorem, well, people read as the Moivre, I read as the Moivre. Using the Moivre's theorem, write down the equivalent form of cos 3 theta plus I sin 3 theta. Hence, show that sin 3 theta is identically equal to 3 sin theta minus 4 sin cube theta. Now, according to the Moivre, okay, according to the Moivre, Z to the n is equal to R to the n cos n theta plus I sin n theta, which this is identical to R into cos theta plus I sin theta, all of this to the power n, which means if I raise all of this to the power n, this n can somehow find itself as a multiple of the power, or as multiple of the angle. Now, in principle, what the question is asking from us is to express this cos 3 theta plus I sin 3 theta in this form, because they said write down the equivalent form according to the Moivre and the Moivre, anyhow we pronounce it. Now, so we are going to try to write cos 3 theta plus I sin 3 theta in that form. It's the start of the question. So in solution, of course, we are going to say cos 3 theta, or we say according to the Moivre, cos 3 theta plus I sin 3 theta should be identical to cos theta plus I sin theta, all of this to the power 3 cubed. Yes. Now, hence, show that sin 3 theta is identically equal to that. Now, if this is correct according to the Moivre, then we should expand this. Now, expanding this, the most accurate method I can imagine right now is via Pascal's triangle. Because if we have to start opening brackets here, we might spend a lot of time here. So we're going to use Pascal's triangle. I particularly love Pascal's triangle a lot. Now, in using Pascal's triangle, we have to draw it out, of course. I'm going to draw it out at this side of the screen for you to see. However, the details on Pascal's triangle is studied under binomial expansion. I think that should be a lower 6th study according to the GCE syllabus. Now, Pascal's triangle is developed as such. We have 1, 1, 1. We have 1, 1 plus 1, 2, 1, that's 1 plus 0. 0 plus 1, you get 1, 1 plus 2, you get 3, 2 plus 1, 3, 1 plus 0, 1. So this is Pascal's triangle. The interesting thing about Pascal's triangle is the very fact that the coefficient of the first element corresponds to the power of the expansion. So which means this is the section that we are interested in as far as Pascal's triangle is concerned. So we are going to expand this using these coefficients. Now, in expanding that, our solution will therefore be, our first coefficient is 1. So we have 1. The first entry, cos theta, is raised to the power 3. Then we have plus our next coefficient, 3. First entry, cos theta, will be raised to the power 2. Second entry is I sine theta will be raised to the power 1. Next coefficient is still 3, 1, 3, 3. So we have 3 first entry cos theta raised to the power 1, of course, and then we have I sine theta, which will now be raised to power 2. Then finally another coefficient of 1. First entry will be power 0, so it doesn't exist. Last entry I sine theta, all of that cubed. At this point we are going to have cos cubed theta plus 3 I is there, so we have I. Then I think I should put the I outside at the furthermost outer part, so we have I into 3 cos squared theta sine theta, yes, like that. Then we have plus, now I is squared, so I squared will be -1. Then we have 3 cos theta sine squared theta, and here we are going to have I cubed. Now if I cube I, if I say I cubed is I times I times I. Now I times I gives me I squared, which is -1, and then we have I this way, so I cubed ends up as -I. I believe that was quite simple. So if I cubed ends up as -I, it means here we are going to have plus -I sine cubed theta. So this will give us going to combine. So we're going to combine the I components, that's the imaginary components, and the real components. So we end up with cos cubed theta. This is real, there's no I on it, there's no imaginary factor, so we get minus 3 cos theta sine squared theta. Now we have the imaginary factor here and here, so I'm going to say plus I into we are going to have 3 cos squared theta sine theta, yes, minus sine cubed theta. Good. Now based on this we do comparison, of course. We try to compare, we try to execute a comparison. We will say the imaginary section should be equal to this imaginary section. Remember what we are trying to prove. We're trying to prove that sine cubed theta can be written as this, can be written as 3 sine theta minus 4 sine cubed theta. That's the objective. So this is my sine 3 theta here. So the imaginary sectors should correspond to each other. Now if that is supposed to be so, then what then can we do? You are going to permit me to erase or to wipe Pascal's triangle the other way. So if the imaginary sections are equal, it means sine, let me just attach my arrows. So it means sine 3 theta can be equal to 3 cos theta or 3 cos squared theta sine theta minus sine cubed theta. Very true, of course, but from trigonometric identities we know that we can write cos squared theta as 1 minus sine squared theta, so we still get sine theta outside minus sine cubed theta. From here it becomes 3 sine theta times 1, so we get 3 sine theta, then we get 3 sine theta times sine squared theta, so we have minus 3 sine cubed theta minus sine cubed theta. This results in, of course, 3 sine theta minus 3 minus 1, of course, minus 4 sine cubed theta, and of course this is sine 3 theta, which is what we were told to prove. Quartz error protractor. Thank you for following. This was Problems under Complex Numbers, June 2024. I am Mr. Genesis. Thanks for following.